Hello students, this is Professor Chalai, and in this video I'm going to show you how to create the potential energy surface for breaking a simple diatomic molecule. So once you've come to chemcompute.org and you've logged in, right, you know you're logged in because it says your name and dashboard up here. To start the calculation, we'll come up to here where it says games/sci4, and we'll use games and we'll click submit a job. And it'll bring up this little screen here where you can draw your molecule. Now, for this video, I'm going to show you how to create like points for Cl2, right? The chlorine molecule. But the simplest way to do this is I'm just going to draw a simple single bond by clicking here and then on the screen, and it creates a single bond. Now, for those of you who did organic chemistry, of course, you know that when you draw something like this, it means that there's a carbon on each end of this bond implicitly not shown. We're not trying to draw organic molecules, so let's remove adding the hydrogens and remove automatically optimized molecule. We don't need those. And we don't want carbons at the end of this bond. We want, well, in my case, chlorine, but you would have different molecules. If your molecule is not on this list, you click X here and you type in your molecule there. But I want chlorine, so I'll click on chlorine and I'll add a chlorine atom to the end of this bond. Doesn't matter what it looks like, I'm just adding, this is Cl2. I remove hydrogens automatically, so we don't add any hydrogens to this molecule. Once you have your diatomic molecule, you click transfer, and it'll bring you down here where it'll show you your molecule. And it'll do some symmetrizing and optimizing, but we don't really need that. So it'll do that automatically, but that's fine. You don't need to use symmetry. You can uncheck that. And then click here where it says manually alter coordinates. Now I want you to calculate the energy of this molecule at various bond lengths. So here's the coordinates for those two atoms, the XYZ coordinates for the two chlorine atoms. The easiest way to calculate it at a certain distance is to set one of the atoms at 0, 0, 0, like that, and then the other atom at 0, 0, whatever number you want the bond length to be. So in my example, I've calculated this for many different lengths already, but I want to do it at 2.05. And the units here are in angstroms, which is 10 to the minus 10 meters. So I want a distance of 2.05 angstroms. Once you have the coordinates that you want to use for this particular calculation, you'll click next, and it'll pull you down here. And you would want to choose the options exactly as I'm showing you here. I'll take a screenshot of this, and you'll have that. But you want to make sure you select package games. Sci4 also work, but let's work with games. You want to give your file a name. I'll do CL2, and because this is at 2.05 angstroms, I'll just put 2.05 angstroms. Each file you want to name it something unique so that you can find it later on if you need to. You can add a comment if you need to. This is the charge of the molecule, which is 0. It's Cl2 molecule. And multiplicity is basically it gives a count of the number of unpaired electrons. The information here says if all the electrons are paired, you should set it to 1. If you have one unpaired electron, you set it to 2. If you have two unpaired electron, you set it to 3, and so on. So we don't have any unpaired electrons in this molecule. So for all your molecules, you should set multiplicity to 1. And you want a single energy. So we'll select single point energy. And we don't really want any of these. Like we could look at the thermodynamics to calculate the delta H and the delta G and so on. But for now, let's just click none because we don't really want any of that. We just want the energy. Later on, we'll look at some of these options. So none. For the basis set, make sure you select this one. It's usually selected by default, 6-31G star. That's how you say that. And then for molecular orbital method, make sure you pick this one right here. ROHF, right? We can talk about that in a bit. And then for DFT functional, we'll select this one right here that says MO6. That's Minnesota functional, made in 2006. That's the one you want to pick for this. For the solvent, we're going to do this in the gas phase, so no solvent. For computer cluster, you can select auto, which will select one of these automatically. Or actually, what I recommend is you click on each one of these separately, and it will give you a queue. So here it says 0.5 minutes queue. Expanse, it says 0.4 minutes. And Jetstream 2, it says 0.0 minutes queue. You pick the one that's fastest. So the queue here is the shortest. Normally Jetstream is actually the fastest. These are three different supercomputers that you can run this calculation on. Typically Jetstream is the fastest. For processor cores, one core is enough. This is a very small calculation, and 1 hour is enough time limit. The smaller you put these, the faster your calculation will get into the queue. So yeah, I want to make sure those are small. If you're doing bigger molecules, you might need 8 cores in 6 hours, but for now, 1 core, 1 hour is fine. And then you click submit job, and it will run this calculation. So if I hit submit job, the calculation will run, and these are small molecules, so the calculations should finish pretty quickly if your queue is not long. And it looks like it already finished because all of these stuff light up here, but you could always scroll back up and make sure it says success, right? The job was run on Jetstream 2 and it was successful. And this is your molecule, and we can talk about all the different cool things down here, but for what we're looking at today is just you need to go to the output file because we want the energy of this molecule, and it's somewhere here in this large output file. The easiest place to find that energy is to take this bar and scroll all the way to the bottom, right? Because it will be somewhere at the end of the calculation. Scroll back up slowly. This is all information about the calculation. Over here, it are the electrostatic moments, basically the dipole moments of the molecule. We don't want that. Scroll up here, atomic spins, we don't want that. The various stuff, let's not talk about them, but let's scroll slowly up until you see something called total energy. It's somewhere near the bottom, but a little bit up. So slowly scroll up, here it is, total energy. So this gives you all the energies of the molecule, the various kinds of energies, 1 electron, 2 electron, repulsion, and so on. What you want is this line that says total energy. That's the total energy of your molecules in something called Hartree atomic units, right? So this is the number that you'd want to copy for your data. So once you've copied your value for the energy, you want to probably put it in Excel or Google Sheets or something to create your graph with it. So I've already run this for many different bond distances. I just did one at 2.05 angstroms, which let me just put another decimal point there. So at 2.05 angstroms, and I didn't copy it. So let me just go back, copy this energy, and I put it at 2.05 angstroms right there. So you'll run these kinds of calculations for various bond lengths that you choose. If just to show you how to do this for another bond distance without going through all those steps again, once you've done one calculation, you can click right here where it says do more calculations, right? And it will take you to this screen again. If you scroll up, here's the same molecule again that you just did the previous calculation on, but we don't want the same geometry, right? We want to change the bond length. Maybe now I want 2.15 angstroms. So I change that and I click next. And then all the settings will probably, it will remember all the settings, but let's change the name for the input file to 2.15 angstroms. Just want to make sure everything is exactly the same as before. It shouldn't change. This time limit one normally changes. I'll select 1 hour again and click submit job, and that would run again at this new geometry. So you don't have to like recreate the molecule from scratch each time. So it'll run. When all this stuff lights up, it's done. If it's taking a long time, you can close the window and come back later. But yep, these calculations should be relatively quickly. It was successful. Go to the output file, scroll all the way to the bottom, and then back up until I find total energy. Right there. So this is a new energy at 2.15 angstrom that I calculated. So I'll just add it here at 2.15 angstroms. So once you've done this for all the points that you want, and you probably would want to do this next step and come back and fill in points like I've just done to make a nice smooth curve. But you want to make sure that you calculate the energy for the atom by itself. So let's start again with do more calculations. And you want, this time, you want the energy, so I click here manually alter coordinates, you want the energy of just one chlorine atom by itself. So I'll delete all of that because I just want one atom, and I click next. Now when you do one atom, let's do single atom, There's a few settings that need to be different. So in a single chlorine atom, the multiplicity is not going to be 1. How many unpaired electrons are there in a single chlorine atom? You draw your Lewis structures and figure it out, but if there's one unpaired electron, so for one unpaired electron, the multiplicity is 2, right? For two unpaired electrons, the multiplicity would be 3, right? So the multiplicity is 2 for one chlorine atom with one unpaired electron. It's still single point, it's still no add-ons, still 6-31G, still ROHF, still MO6, no solvent, jet stream 2, which is the lowest Q, and time limit of 1 hour. But this will be the calculation for just one atom. You hit submit job, and it will submit that job and run it. And this should be even faster calculation because it's half the molecule, right? It's just one atom. All right, looks like it's done. You scroll back up, right? It was successful. You go to the output file, scroll all the way down, and then back up to total energy. And this is the total energy for one atom, which you want to put in your table somewhere. So I'm just going to put it right here, one atom. The reason why, one atom energy. The energies here are all in atomic units, or Hartree atomic units. So I could put, actually I don't want text in there, just the number. The reason why we do this is because when you break the bond apart, you'll get two atoms, right? But two atoms by themselves. So if I take this energy and I multiply it by 2, so equal to this number multiplied by 2, this is the energy of 2 single atoms by itself, right? One atom multiplied by 2 is just 2 single atoms by itself. So I want to rescale all of these energy. I want to subtract out this number because these are the energies for the molecule binded together, whereas this is the energy of one atom or 2 atoms by themselves. So I take this original number minus this energy right here, and now I get exactly just the bond energy. I'm going to put dollar signs around this D1 so that this number doesn't change here. And then I'll just copy this and paste it for all the cells that I have, like that. So now I have just the, I just have the bond energy because I've subtracted out the energy for the atoms by themselves, right? And then I want this energy, so bond energy, but I want it in, let's say, kilojoules per mole, right? So I've done this as well. To go from atomic units to kilojoules per mole, you multiply by 2,625. You can look up that number to scale from atomic units. But I take this number equal to that number and I times at 26,025. And so this is my bond energy now in kilojoules per mole. Let's reduce the number of decimal places there so it looks better. So now this is what we want to plot on the y-axis, your bond energy. So your x-axis is your length, your y-axis is your bond energy. I guess I can't do it that way. I'll select all of that and I'll create a plot with it, and it doesn't make a nice plot. So I'm just going to copy all of this over to a nice space over here, and I'll do paste just the values. And I'll copy all of this over here and paste just the values so that I have them right next to each other so that I could create the plot nicely. So I have length, bond energy, and I create my chart, and there it is. Now the y-axis obviously goes way too high, right? We just want the negative part of this graph. So in my chart axis, I haven't used this, the vertical axis, right? The maximum value, I probably just want like 100 kilojoules. Okay, maybe 200. Just play around with this number until I see like this flat part of the curve. The minimum, just save it as auto. And there's my curve. Now it's not quite smooth, right? There's a couple of points down here that are a little bit weird, but I'll figure that out later. So this is my bond potential energy surface for the bond dissociation of Cl2. Why does it go above 0 here? We can talk about that in class, but when it separates, this is the 0 energy, and so the lowest point here, which is it looks like negative 224.4 kilojoules per mole, that's the bond dissociation energy. That's the energy you need to break this bond and separate it to infinity. And so you'll include this in your report.